Here are the answers to ChemActivity 21, partial charge. Remember, the goal in this activity is to use average valence electron energy to figure out how unequally the electrons are shared in a bond, and as a result, where does the partial positive and where does the partial negative charge reside within the bond on the different atoms. Critical thinking question 1 wants us to figure out the meaning of the 7, the 6, the 2 in equation 6, and why use the negative signs. In order to better understand this, it's useful to have a Lewis structure for hydrogen fluoride. Notice in the Lewis structure that fluorine has 6 unshared electrons, and that fluorine has 2 shared electrons, and that hydrogen only has the 2 shared electrons. Partial charge is essentially the leftover charge after the electrons on the atom have canceled the core charge. So if we start looking at the equation, you'll notice that the 7 represents the core charge of the fluorine, or 7 valence electrons, but it's probably better to think of it as the core charge. In the Lewis structure, fluorine has 6 electrons that it doesn't share, so that's a -6 charge that works toward canceling out the positive 7 core charge. And then in the Lewis structure, the fluorine has 2 electrons that it does share. Using average valence electron energy, we figure out that the fluorine has those 2 electrons 63.7% of the time, so it gets credit for 63.7% of 2 electrons, or an additional -1.27 charge. When you take the positive 7 core charge and subtract the -6 for the electrons that fluorine has to itself, and subtract the 1.27 that fluorine shares, you come up with an overall charge of -0.27. The negative signs here are present because we're subtracting 1 from the positive 7 core charge for each electron that fluorine has in the Lewis structure, and then looking at how much charge is left on the fluorine after that. The other way you can look at the negative signs here is that they're present because electrons have a negative charge. In question 2, we have to talk about how average valence electron energy can be used to determine which atom has the partial negative charge. Very simply, the atom with the greater average valence electron energy has the electrons a greater amount of the time because it has a tighter pull on them, so it ends up with a partially negative charge. In number 3, we have to explain why the partial charge on hydrogen is equal to but opposite to the partial charge on fluorine. This is just because the total charge on the hydrogen fluoride molecule still has to be 0. That's one of our pieces of our definition of the molecule. And therefore, if the fluorine has a little bit of partial negative charge, the hydrogen has to have an equal amount of partial positive charge so that it adds back to 0 again. And this is going to be true in number 4 all the time. Anytime you have a diatomic molecule, the partial charge on one atom in the molecule has to be equal and opposite to the partial charge on the other atom in the molecule, or the sum of the partial charges has to add up to 0 to make sure that the overall molecule still has no charge like we would expect. In the first exercise, we need to go through the same process that was done in the book for hydrogen fluoride, but do this for hydrogen bromide based upon the average valence electron energies for bromine and hydrogen. So the first thing I need to do is calculate the electron pull from bromine. The electron pull here is determined by taking the average valence electron energy for bromine and dividing that by the sum of the average valence electron energies for bromine and hydrogen. And what we learn is that bromine has the electrons 53.9% of the time. So the partial charge on bromine is the positive 7, which is the core charge on bromine, minus the 6 electrons that bromine has to itself in the Lewis structure, minus 53.9% of the 2 electrons that bromine shares, or a -0.077. Knowing that the hydrogen has to have a partial charge that perfectly counteracts the negative partial charge on bromine, we can very quickly determine that the partial charge on hydrogen is a positive 0.77, or positive 0.77. And this is reasonably close to the value in Table 1. Keep in mind that in Table 1 they used a much more complicated method than we did, so their value is probably more accurate, but ours made a pretty good approximation. And now we go through the same calculation to do this with bromine in Br2. The thing that changes here is that because both of the atoms are the same, when they share the electrons, they share them at exactly 50%. So the partial charge on bromine in the Br2 molecule is 0, but that makes perfect sense because the two bromine atoms share the electrons equally, so neither atom should end up with a charge. And this idea has to hold true for all of our homonuclear diatomic molecules. These are the molecules where two atoms of the same element have formed a bond, and the partial charges on these atoms has to be 0 in every case due to the fact that the electrons are shared equally because the two atoms sharing the electron are equal. And lastly, number 4, in the molecule AB, if the partial charge on A is 0.13, then the partial charge on B has to exactly counteract that so that it adds back up to 0. So the partial charge on B has to be equal but opposite, or negative 0.13. For the next series of questions, we have to look at some average valence electron energies and some partial charges and try to explain some trends here. You'll notice that as you go down Table 1, we're essentially going down the 7th column of your periodic table: fluorine, chlorine, bromine, and iodine. And as we do that, the average valence electron energy on hydrogen stays the same. Of the halogens, fluorine has the largest average valence electron energy. Iodine has the smallest average valence electron energy. So we have to explain in number 5 why it is reasonable that the hydrogen atom has a positive partial charge and the chlorine has a negative partial charge in HCl. That's just as simple as chlorine having a greater average valence electron energy than hydrogen, so the shared electrons spend a greater amount of time with the chlorine. In number 6, we have to figure out why it is that the hydrogen atom has a greater amount of partial positive charge in HF than it does in HCl. And this is just the difference in average valence electron energies. The difference between hydrogen and fluorine is greater than the difference between hydrogen and chlorine. So the sharing is going to be more unequal in a hydrogen fluoride bond than it is in a hydrogen chloride bond. And the more uneven the sharing, the greater the value for the partial charges. In number 7, we have to look at Table 3, and our original comparison here is between methane and tetrafluoromethane. And we're asked to explain how carbon can be negative in one molecule but positive in another. And it turns out that in one molecule, carbon has the higher of the two average valence electron energies, and in the other molecule, it has the lower of the two average valence electron energies. And it will always be the case that the atom with the higher of the two average valence electron energies will carry the negative charge. So in methane, where carbon has the higher of the two average valence electron energies, it comes out negative, and in tetrafluoromethane, where fluorine has a higher average valence electron energy than carbon, carbon ends up picking up a positive charge. We're now going to make the same comparison about the nitrogen atom in ammonia and the nitrogen atom in trifluoronitrogen, which is the next little set of compounds. And again, we see the same general trend here. Nitrogen has a positive partial charge in NH3 because nitrogen has a greater average valence electron energy than hydrogen, but in the trifluoronitrogen, fluorine has the greater average valence electron energy. It hogs the electrons more of the time, leaving nitrogen with a partial positive charge. Very similar situation in number 9, looking at water and dihydrogen sulfide. In water, oxygen has a partially negative charge, because it has the larger of the two average valence electron energies. And in dihydrogen sulfide, the sulfur carries the partial negative charge because it has a greater average valence electron energy than hydrogen. And lastly, why is the oxygen in water more negatively charged than the sulfur in H2S? The difference in average valence electron energies is greater between the hydrogen and oxygen than it is between the hydrogen and sulfur. Remember, when you're looking at these situations, the two things to look for is which atom has the larger AVEE. It's going to get the partial negative charge. And you have to look at the difference in average valence electron energies between the two elements. The bigger the difference is, the greater the value for the partial charges. Number 10 just wants you to add up the sum of all the partial charges on the atoms in each of the following. So we have to use the data in Table 3, and we have to think about how many of each atom are present. Methane has 4 hydrogen atoms, so we take 4 times the partial charge on hydrogen, add that to 1 times the partial charge on carbon, we get our answer. For water, we do 2 times the partial charge on hydrogen in water, plus 1 times the partial charge on oxygen, we get a negative 0.001. For all practical purposes, these two answers really are 0. With the ammonium ion, we have 4 hydrogen atoms and 1 nitrogen atom, and when we add up the partial charges, we get a 1.002. And for carbonate, we have 1 carbon and 3 oxygens. Adding the whole thing up, we get 1.999. In terms of a relationship, it shouldn't come as any big surprise here that for a molecule, regardless of how many atoms are in the molecule, the sum of the partial charges has to be 0. And for a polyatomic ion, the sum of the partial charges should add up to be the charge on that particular polyatomic ion.